Hello guys, I hope you are doing well. In this session, I'll be explaining the chapter 4, the first section of chapter 4. You know that chapter 4 is all about two sections. The first section will be talking about the thermochemistry. We'll be talking about the specific heat. Define the thermochemistry, define the heat, temperature, and then we'll be talking about the specific heat, and at the end of the section we'll be talking about the enthalpy of the reaction, the enthalpy of formation and combustion as well. The second section will be about the driving forces of the reaction, and we'll be talking about the spontaneity of the reactions, guys. The first section is all about the thermochemistry. Let us define the thermochemistry, and then we'll be talking about the enthalpy of the reaction in detail. Guys, thermo is a term which represents or refers to what? Refers to the heat. Thermal, to the heat. So we'll be talking about any processes that will occur, whether it's physical or chemical. There will be changes in heat of the system. That's why we will be talking about the thermochemistry for representation of the how much heat absorbed or released through a process, through a chemical or physical changes. A thermochemistry is a branch of chemistry which deals with what? With the amount of heat which transferred between the systems, through or during a chemical process or a physical change. Is a study of the transfer of energy as heat that accompany chemical or we can say combustion or burning reactions, and physical changes like melting or freezing. So whether a physical change or a chemical reactions, there will be changes in the heat of the system. The thermochemistry talks about the field that relates to the changes of the heat of the system due to the chemical reactions and the physical changes. We may be wondering how to measure the amount of heat absorbed or released through a system. There are several methods to represent or to calculate the heat of the reactions, but in our curriculum talks about one of them, which is a calorimeter. A calorimeter is what? Is this device, guys. This device is a calorimeter. A calorimeter is a device which measures the heat of the processes or chemical reactions or physical changes as well. Let me somehow explain the figure to you in order to understand the working mechanism of the calorimeter. Guys, a calorimeter, first of all, the main unit is what we have. We have a dish sample. A dish sample, we add the chemicals to that dish sample to react. So we add the reactants to this dish sample. Reactant, those chemicals that we want to react to produce the product is we add to the dish sample. And then this dish sample, we have around the dish sample, we have a steel bump, the steel bump. This steel bump allows the heat to pass in between, or to be transferred in between the dish sample to the surrounding water. We'll be talking in the surrounding there is water, but does not allow the mixing, physical mixing, or allows the passage of the heat, but does not allow the passage of mass. And around the sample dish we have water. So this all around here we have water molecules. And a stirrer continuously stirring this water in order to be all the side of the water to have the same temperature or the same heat. And then, guys, the outside of this chamber is an insulated container. Insulated means does not allow the passage of heat and mass as well. In order to measure the temperature of the water, we inserted a thermometer. A thermometer is a device which uses to measure the temperature of the systems. Any reaction in chemistry, guys, we need an ignition source. So the ignition wire must be used to ignite the reactants, to combust the amount of the reactants. How it works, guys? At the beginning of the reaction, though we are not able, guys, to measure the heat directly. How to know whether the process is exothermic or endothermic? At the start point, and there will be a final point. At the beginning of the reaction, we have to measure the temperature of the surrounding water through the thermometer. Suppose it's 25 Celsius initial. And after the completion of the reaction, all the reactants converted to product, we use the thermometer to measure the final temperature. If the final temperature, for example, is 32 Celsius, 25 to 32 means the temperature increases. How the temperature increases? Because this reaction tells us that the reaction releases heat to the surrounding water and warms up the water molecules. In this case, it will be an exothermic process. We'll be able to determine the process is exothermic. But if the final temperature is 20 Celsius, cooled down the water, that means it absorbed heat from the surrounding water to process, to continue the reaction. So in this case, this will be endothermic. Why? Because absorbed heat from the surrounding. And due to having different temperatures, we will be able to know that a reaction occurs, and that reaction, whether it releases an amount of heat to the surrounding or absorbs the heat from the surrounding. That's the working mechanism of the combustion calorimeter. This is the combustion calorimeter, which we add something and combust it. We will be able, usually the combustion processes are exothermic, that warm up the processes or warm up the surrounding, guys. That was the working mechanism of the combustion calorimeter. We have discussed about the combustion of the calorimeter, guys. The data collected from calorimetric experiments are temperature change. We can collect the temperature changes because an energy change cannot be measured directly. We cannot measure the energy change directly. But temperature, which is affected by the transfer of energy as heat between the systems, whether from this sample to the surrounding water or from the water to the sample, is directly measurable. We can measure it and represents measure through this thermometer, guys. Why does temperature change? What's the reason behind changing temperature? The answer is that because energy is transferred from a higher temperature to a lower temperature spontaneously. Whenever we have two objects, we'll be talking about this in heat. the energy spontaneously transfer from the hotter one to the colder one. That's why if the reaction is exothermic, spontaneously the heat from the reaction goes to the surrounding water. If it's endothermic, spontaneously from the surrounding absorb heat in order to process. From the water goes to the reaction. Let us define the terms of temperature and heat. We may be confusing. What's the difference between them? They are almost related with each other, but they are different. Temperature, guys, is a scale of measurement. It's not a quantity. But heat is an amount, is a quantity. So let us define both of them in detail. Temperature is a scale of measurement which measures what? The average kinetic energy of the particles in a sample of matter. In any system, what the temperature represents? It represents what's the degree of the movement of particles in a sample of matter. For example, if we have two samples, two systems with the same amount, but one of them has a 25 Celsius, the other is 50 Celsius. The 50 Celsius represents what? There is a higher kinetic energy in this system and a higher motion of particles in the system than the lower temperature. So whenever the temperature increases, there will be a higher movement between the particles of that system, kinetic energy will increase, but whenever it reduces, the temperature represents a lower motion of the particles in the system. The greater the kinetic energy of the particles in a sample, the hotter it feels. So which one is hotter? Of course, the 50 is hotter than this is colder one, 25 Celsius, if we compare them together. For the calculation, guys, in thermochemistry, the Celsius and the Kelvin can be used in both, Celsius and Kelvin. What's the conversion between Celsius and Kelvin? It's both given. If you want to convert Celsius into Kelvin, just add the Celsius with 273. But if you want to convert the Kelvin to Celsius, subtract the 273 from the Kelvin, you will get the Celsius. But if the change in temperature, we will be facing change in temperature in specific heat, the degree in Celsius and Kelvin has no difference. Why? Because 15 or 0 Celsius, which is 273 Kelvin, 25 Celsius, which is 298 Kelvin, this difference is 25, and this difference is 25 as well. So the difference has no, change delta of temperature in Celsius and Kelvin is equal. Let us talk about the heat. The amount of energy transferred as heat, measured by joules. So what's heat, guys? What's heat? Heat of the system. The temperature, it was a scale of measurement which measures the average kinetic energy of the samples in a system, of particles in a system. But heat is an amount of energy, is a type of energy which can be transferred between the systems due to of having different temperature. So, transferred between the sample of matter because of difference in their temperatures. Joule is a SI unit of heat as well for the other types of energy. And guys, the joule is derivative from the unit of force and length, which represent here. Force, which is Newton, multiply the length, which is meter, and the Newton is kilogram meter per second square, and then kilogram meter per second square multiply the meter, we'll get kilogram meter square second square, which is the unit of joule. Energy transferred as heat always moves spontaneously from matter at a higher temperature to the matter at a lower temperature. So the energy transferred between the matter spontaneously from which to which, from the hotter object to the colder object is. Have a look, guys, in this figure here we have got a water, an amount of water, and adding heat to the piece of metal. A piece of metal is given in, and we provide heat, we heated a piece of metal. The temperature of the water is 21.2 Celsius almost in the first. But in the second, guys, as we immerse it, the hot object, so this is hot, this is cold. As we add the hot object into the cold, the amount of heat transfers spontaneously. Heat transfers spontaneously from the hotter object to the colder object. The hotter object is in a higher temperature. The colder object is in the lower temperature. The transferring of heat from the hotter to the colder continues till they reach to the equilibrium position, which both systems or both objects they do have the same temperature. Here the temperature increases to 35.4. What's this? That's the sign of what? The heat transferred from this object to this piece of metal to the water and warms the water. That's the representation of heat. In this between, the amount of energy transferred from the hotter to the cold we call as heat. That's the heat, and measure it by the joule. The difference between heat and temperature, guys, the unit of heat is joule, but the unit of temperature is Celsius or Kelvin. We have other units, but we do not use in our curriculum. The heat represents what? Energy transferred between samples of matter due to having different temperature. But the temperature is what? Measures the average kinetic energy of particles in the sample. Energy as heat moves spontaneously from a matter at higher temperature to the lower temperatures. As temperature increases, average kinetic energy of particles increase and the samples becomes hot. The conversion between Kelvin and Celsius is given 273 plus Celsius results the Kelvin. Specific heat, Cp. Guys, in order to understand the Cp, first let us talk about the amount of heat that transfer between the samples depends on what? The quantity of energy transferred as heat during the Q depends on three factors. First, the nature of the chemicals, which we call as the Cp. We will define Cp. The nature of the materials, guys. In nature, we have some chemicals or some substances, some elements, they transfer heat more than the others. A simple example, for example, aluminum or copper or metals in general, they conduct or they transfer heat more than the non-metals usually. But the Cp is the representation of that nature, and we will define the Cp of the materials. The second is the amount of those materials, of the samples. Of course, as 10 grams compared to 100 grams, Which one will carry more heat? The 100 grams. So as we increase the amount, that increases the holding capacity for heat. The size of the temperature change. If the two objects they are close to each other, there will not be a fast or a quick transferring of heat. 20, 21. So they are not far from each other. But if the two objects somehow far from each other, 20, 75, a hot object with a cold one, so the transferring of the heat will be increasing, the speed of the transferring. So the delta T, the mass, and the Cp are those factors that influence the transferring of amount of heat between the samples. Guys, in order to understand how the substances they have reactivity with the heats, or they deal with the absorption capacities of those substances to the heat, and how they absorb, how they release the heat is, in our book provides an example. The example says that when we have iron and Ag, silver. Suppose for both we have got 1 gram of each sample. 1 gram. 1 gram for iron and 1 gram of Ag. Both we added heat, or we heated to 100 Celsius and then cooled till 50 Celsius. We provide heat to those samples, to those grams, heated the both samples till 100 Celsius, and then added both into water, cooled down, wait till 50 Celsius. How much heat from those samples released to the surrounding water? The amount of heat which released by the iron, it was almost 22.5 joules. But the amount of the Ag, 11.8 joules. Almost twice as the Ag. The iron is almost twice as the Ag. What this represents? It represents that those two samples, they have same masses, but the iron absorbed a higher amount of heat and then release it to the surrounding a higher amount than the Ag, almost twice as the Ag. This is related to the nature of those substances, to the absorption for heat. Absorption capacity of iron here is more than the Ag. And this absorption capacity we call as the specific heat. So the difference depends on metals' different capacities for absorbing this energy, guys. Absorbing capacity of those metals are different. A quantity called specific heat can be used to compare heat absorption capacities for different materials. We will be talking in detail about the specific heat, but the specific heat is a quantity which we use to represent the absorption capacity of the substances. So specific heat, I will be explaining specific heat in a model, guys, to you, so you will not forget the definition. 1 gram of any sample, a sample of matter, iron, Ag, Zn, aluminum, any matter, guys. If this gram is at 20 Celsius, we want to increase the temperature to 21 Celsius. Kelvin or Celsius doesn't matter. Guys, in order to increase the temperature of 1 gram of a sample by 1 Celsius or 1 Kelvin, only 1, we need an amount of heat, and that heat is a specific heat. So what's a specific heat? Specific heat is the amount of energy required to raise the temperature of 1 gram of any sample by 1 Celsius or 1 Kelvin. Is the amount of energy required to raise the temperature of 1 gram of a sample by 1 Celsius or 1 Kelvin. The changes has no difference. That's why in both scales we can use the changes. So guys, this specific heat, as we explained it, and the specific heat represents the absorption capacity of the materials. The absorption capacities. The temperature difference as measured in either Celsius degree or Kelvin is the same. Values of specific heat are usually given in units of joule per gram Celsius, but we have got 3 units of specific heat. 3 units of specific heat. You have to memorize those units. Joule per gram Celsius, joule per gram Kelvin, or calorie per gram Celsius. These are the units which are given, and you have to memorize those units. How to calculate the specific heat for the reaction or for the substances? Guys, specific heat represents by Cp. The Cp, why Cp? We measure the specific heat for any sample at constant pressure. That's why the subscript of P represent or refers to what? To the constant pressure. Constant pressure. Specific heat, Cp, is the specific heat at a given pressure or at a specific pressure. Must be constant, the pressure. Is equal to the Q. Q is what? Is the energy lost or gained. Can be lost or gained, and must be in joule, guys. Refers to the unit of Cp. M is the mass, must be in gram always. And the delta T equals to what? Initial and final change of the initial and final. T final minus T initial. And the unit depends on the unit of Cp, can be Celsius or Kelvin, but the one that we use more commonly is the Kelvin one. And how to calculate the Q, the heat, Cp m delta T can be used to calculate the Q. Here the table is given, table 1. This table 1, several substances are given with the specific heat, and the specific heat is in joule per gram Kelvin. Joule per gram Kelvin. So whenever it's joule per gram Kelvin, the heat must be in joule, the mass must be in gram, the delta T, the T must be in Kelvin. What we have to memorize? Only the liquid water, which is 4.18 joule per gram Kelvin. So you have to memorize for water, liquid water, not gaseous, not solid. Let us solve a sample problem, guys. A 4 gram sample of, so the gram is given, the mass. delta T is given for 314 minus 274. This will be the change is 40 Kelvin. Was found to have to absorb 32 joules. What's the specific heat of this type of glass, CP? How much energy will the slim sample gain when it has the delta T of this? Simply, guys, Cp is equal to Q per m delta T. So the Q is 32 joules. The mass is 4 grams. Delta T is 40. You get 0.2 joule per gram Kelvin. Part B, Q when delta T is this, okay? Q is equal to Cp multiply m delta T. M 4 grams, delta T is this, so it will be 24 joules, the Q. The practice, here we have got another question. Determine the specific heat, Cp, when 35 grams is given mass, 48 joules, the delta T is 313 minus 293. Guys, for the solution of this, simply Cp is equal to Q over m delta T. Q is 48 joules, which is given, m 35 grams, and delta T is equal to 20. So the Cp is equal to 0.069 joule per gram Kelvin. The second question in the practice, guys, it appears in ministerial exam more commonly. Most of the round is whenever they would like to provide questions in CP, appears the second practice. The second practice, what we have, 980 kilojoules, 6.2 liters of water, and the T initial. The requirement is what? Is the T final. Guys, Cp is equal to Q over m delta T. We need T final. So take the delta T to other side. Delta T Cpm is equal to Q. Delta T is equal to Q over Cpm. Open the delta T, T final minus T initial is equal to Q over Cpm, or T final alone is equal to Q over Cpm plus T initial. That will be the arrangement of the equation. Q is given, but it's not given in joule. That's you have to change it. By what? By multiplying 2,000, you'll get 980,000 joules. The mass, 6.2 liters is given, guys. Keep in mind that the mass for, here we have got a note, only for water, 1 liter is equal to 1 kilogram. The volume is equal to the mass. So instead of 6.2 liters of water, we can use 6.2 kilograms of water, and 6.2 kilograms of water must be converted to grams, will result as 6,200 grams. So the question is, ready, the quantities, 980,000 kilojoules, 6,200 grams, 4.18 the Cp of water, and then we'll be able to calculate delta T. Delta T is equal to 38 K. So the T final is equal to what? Delta T plus T initial. So is equal what? 38 plus 291 results 329 Kelvin. In ministerial exam question said the T final is equal to 56 Celsius. This is true also. Why? Because when we convert this into Celsius, it will be 56 Celsius. That's the correct answer as well. Water has an extremely high specific heat. The specific heat of water is high. That's the calculation for the specific heats, guys. There will be a type of the question in ministerial exam based on the relation Cp is equal to Q over M delta T. Said when we have two samples of matter with the same Cp and the same mass. Same Cp and the same mass. So these two are the same. Which one will absorb more amount of energy? The one that we provide a high amount of heat, the one that we provide a low amount of heat, both they absorb equally or none of them. Guys, the relation absorption of heat is Q. Q, how it changes to the absorption capacity, which is the Cp, is directly proportional. So the one that we heated more absorb high amount of heat, despite of equalizing the Cps. They have the same capacities, but when we provide more, it absorbs more. That's the answer. Another type of question, two substances with equal mass, but different CPs. Which one represents a higher change in temperature? Which one? Guys, the Cp, how it changes with delta T? Inversely proportional. So the one that has a higher Cp represents a lower change in delta T. The one represents a lower or has a lower Cp represents a higher delta T. That's the questions depends on the mathematical relations of those quantities in the equation. We will be talking about the enthalpy of reaction. The enthalpy of reaction is very important and an important topic in section 1 of chapter 4. Guys, the enthalpy is a term, is the same as the heat of reactions. So it's not different than the heat of the reaction. But what's the enthalpy? Let us define it and how we can calculate the enthalpy. The energy absorbed as heat during a chemical reaction at constant pressure is represented by delta H. What's delta H? H is a symbol for the enthalpy. H is a symbol for a quantity called what? Call it enthalpy. So the amount of the heat that transferred between two systems, measure it by what? By the enthalpy. Enthalpy. Only change in enthalpy can be measured. Delta H is read as what? As the enthalpy change. Why? Because, guys, enthalpy is a state function, which means it depends on the initial and final point of the reaction. Enthalpy is a state function. State function means it depends on 2 points, the beginning and the final. Change. In one point, we cannot be able to determine the enthalpy. So what's the enthalpy change? Is the amount of energy absorbed or released by a system as heat during a process at constant pressure. We measure the enthalpy at constant pressures. And this is the enthalpy of reaction, enthalpy changes. Is the amount of heat which releases exo or absorbed during a process at constant pressure. Enthalpy change can be represented by enthalpy of the product, which is the final, minus enthalpy of the reactant. So the product is the final, and the reactant is the initial. Delta H is equal to enthalpy of product minus enthalpy of the reactant. Enthalpy of reaction or heat of reaction is a quantity of energy transferred as heat during a chemical change. Quantity of heat that transferred between the systems during a chemical reaction we call as the enthalpy of reaction, or we sometimes use the heat of reaction for the enthalpy of reactions. Guys, we have got two courses of reactions. Two courses. One exothermic, the other endothermic. Here we will be explaining the differences between those two courses, the position of reactant and product in terms of energy levels, and then the stability of both as well. Let us examine the exothermic courses. Guys, exothermic means releasing heat. The reactant, suppose this is the enthalpy, 0. Reactant is in the 0. Where should be the position of product A or B for the exothermic? Logically, exothermic means what? Means the reactant releases heat to reach to the product. So what will happen to the final position of energy? Of course, must be lower than the initial. Of course, must be lower than the initial. That's why the B minus 50 kilojoules should be the correct answer. A lower position than the reactant. This will be the product position. So keep in mind, in order to draw a relation of, or a graph or a path of the exothermic path, we need two lines. A vertical one which represents the enthalpy change, the horizontal one which represents the course of reaction in time. The time of the reaction, at the beginning, at the midpoint, at the end of the reaction. Guys, always, as you can see, reactant, the product for exothermic. So, you have to know these informations. For exothermic course of reaction, always E reactant higher than the E product. Or enthalpy of the reactant, energy of the reactant is in a higher position than the product. Second, delta H is equal to E product minus E reactant. For example, here 100 kilojoules. This is 30 kilojoules. The product is what? 30. Minus reactant is what? 100. Results what? Minus 70 kilojoules. For an exothermic course, always the enthalpy change is what? Is negative. Results a negative value. Second. Third, in terms of stability. The stability in chemistry, we mean a position of energy or a position of a substance which has the least energy position is the most stable. So least energy is equal to the most stable. Highest energy, the least stable. So as we increase the amount of energy in a system, the stability decreases, and vice versa. The energy is inversely with the stability. So in this between, which of them has the more stability? The one with the lower position of energy. The lower position of energy, 30 with 100 kilojoule, of course, product. So the product is more stable than reactant. Of course, the product is more stable than the reactant. Always for what? For an exothermic path of reaction. These are the important pointers you have to know that. Graphic shows the course of exothermic reaction. Initial energy of reactant is greater than the final energy of product. The enthalpy product is more stable than the reactant. Stability is inversely proportional with energy. You have to know this, guys. Examples, guys, for the exothermic reactions: formation of H2O results at minus 483.6 kilojoules, or formation of CO2 as well, minus 393.5 kilojoules. Usually, guys, for most reactions, we have some exception we will be talking about. Formation reactions are exothermic. Formation reactions or formation of bonds, most of the formations are what are exothermic processes. Let us talk about the endothermic course of reaction. Endothermic is just the opposite of the exothermic, guys. Graph shows the course of endothermic. Initial energy of the reactant is lower than the final energy of product. Guys, endothermic means a reactant is in a position of energy. We add heat, absorb heat to reach to the product. So the product must be in a higher position of energy. Reach to the product with the higher position of energy. That's why always reactant must be lower than the product. The reactant here 30 kilojoules, the product 100 kilojoules. Just reverse of the exothermic. Guys, we can conclude these informations. E of product is higher than E of reactant. As E of product is higher than the E of reactant, so the reactant is more stable than the product. Why? Because the reactant is in a lower position of energy. And the delta H results a positive value. Why? Because delta H is equal to final, which is 100, minus initial, which is 30, you'll get the positive value of delta H. So always the enthalpy for endothermic course is positive. And in terms of stability, we said the reactant is more stable than the product, guys. Or to not forget, guys, the shape of the graph of exothermic is just like a Z, okay? A Z. But the shape of the endothermic is just like S. So, if it's Z, if it's S, Z, reactant, product. Reactant, product. Reactant goes to the product, lowers. This is exo. But reactant elevates to the product, endo. Just simply to not forget the enthalpy courses. Those examples for the endothermic, the decomposition of H2O, just the reverse of the above, represents a 483 kilojoules, or needs a 483 kilojoules. Decomposition of CO2 needs 393.5 kilojoules. So guys, usually the breaking processes are endothermic. Breaking processes are endothermic. Formation processes or formation of bonds are exothermic. Breaking bonds are endothermic. Thermochemical equations. Guys, the normal equations, usually when we write the formula equation, does not represent any information about the heat. But what do we mean by the thermochemical equation? In thermochemical equation, we represent the heat quantity of energy released or absorbed through a reaction. So whenever we want to write the thermochemical equation, and for this, from now on, we'll write the equations in the form of thermochemical equation, we have to mention the heat of the system, of the reaction, whether it's positive or negative. We have two ways to represent that. So this is a thermochemical equation. Why? Because an amount of energy is represents. A thermochemical equation, because an amount of energy represents. Thermochemical equation, an amount of energy represents. But if it's not representing the amount of energy, whether included in the reaction or as enthalpy change, that does not represent a thermochemical equation. How to know whether it's indoor or exo? We have two notes. If the amount of energy is written in the reactant side, if the amount of energy is written in the reactant side, like what? Like here, the first one. The reaction is endothermic. So, energy in reactant, endothermic. But energy in product represents the reaction is exothermic. Endothermic and exothermic. A plus energy to form B is what is endo, because energy is in the reactant. B plus energy to form A is exo. Sorry, B plus energy. So here we have the energy in the product, which is exothermic. Whenever the energy is in the product, exo, energy in the reactant, endo. Okay, guys. How about the other way, in the form of enthalpy change? If it's given in the form of enthalpy change, a positive value represents what? Endothermic. A negative value represents exothermic. So, as this, delta H is equal to negative 483, exothermic. Delta H is equal to 483, endothermic. That's how we can represent the endo and exo. We'll be talking about the factors influencing the enthalpy of reaction. There are several factors that influence the enthalpy of reaction. The first one is a physical state. A physical state of reactant and product always must be included in a thermochemical equation. Why? Because the states of reactant and product influence the overall amount of energy exchanged. Example, guys, formation of 2 moles of liquid water, formation of 2 moles of liquid water releases more energy than 2 moles of gaseous water. Have a look on this. 2 moles of gaseous, 2 moles of liquid. Which one releases more? Of course, the one of liquid. Why? Because due to a physical status, or a more for physical change, guys, whenever you want to boil H2O gas, or H2O liquid, or H2O solid. So H2O liquid to become H2O gas, boil it, evaporation, H2O gas. It's not logic to say the H2O liquid and H2O solid, in order to boil them and evaporate them, to be gaseous, to be vapor, we need the same amount of heat. No. This directly can be converted to gaseous. So we need the amount of, but the solid, we have to convert it into H2O liquid, and then H2O liquid goes to the H2O gas. So the path of this is longer, the path of the other is shorter. A longer path needs more energy, or absorbs more energy, or releases more energy. That's why the physical states must be represented. Different physical states represents different enthalpies. This is the first factor that influences the enthalpy. Okay guys, the reactions in the thermochemical equations, whenever we multiply the reaction by any factor, any number, we have to multiply the enthalpy by the same factor or by the same number. Here we multiplied the equation by half, or we can say divided by 2. The H2 divide by multiply by half, or divide by 2, 1, and then this is 1 over 2, and H2O 1 as well, and then the enthalpy must be divided by 2 as well with the thermochemical equation. So we have to know that we multiply the equation. Do not forget to multiply the enthalpy always. Multiply the reaction by 4, so you'll get 4 hydrogen, 2 oxygen, 4 H2O, and then 4 multiplied by the above enthalpy. Keep in mind that do not forget to multiply the enthalpy amount by the same factor. Another point on the enthalpy of the reactions, guys. Whenever we have reactions, usually the reactions are reversible reactions. If in a direction the enthalpy is negative, when we reverse the reaction, the sign of enthalpy will be reversed. From negative it becomes positive, or if it's positive it becomes negative. The enthalpy, another factor which the enthalpy depends on, we said enthalpy depends on the amount of reactant and product, and enthalpy depends on the physical status. The third factor which enthalpy depends on is the pressure. So the enthalpy changes by changing the pressure of the system. But guys, keep in mind, you may be confused about the temperature and pressure. The enthalpy changes by pressure, but is not significantly affected by changing temperature. So temperature cannot be taken into consideration of one of the factors that affects the enthalpy of the reactions, guys. Here are some notes. We have discussed about some of them, and the first one, the coefficient in the thermochemical equation, we will count as the moles rather than as molecules. Why? What's the difference between them? The difference is that, guys, I can say 1 over 2 H2O. This is for the mole. Mole represents the amount of something. Amount can be in fraction, can be in half, can be in quarter, can be any number. But I cannot say H2O, 1 over 2 H2O molecule. We do not have half molecule of something. There should be a whole number for the molecules. Molecule represent the structure, the composition or formation of a compound or any substances. So we will take the coefficient in the thermochemical equation as moles, as the amount, not as molecule. The second one said the physical state must be mentioned. We talked about that. Physical state plays an important role in determining the enthalpy. Why? Because different physical states, there will be different enthalpies. The change in enthalpy represented by a thermochemical equation is directly proportional to the number of the amounts of a mole of reactant and product. As the amount of reactant and product increase, there will be more enthalpies. As it decreases, there will be a lower enthalpy. We talked about that. And the last one said the enthalpy is not influenced by the temperature. So let us talk about the stability. We will talk about the enthalpy of formation and then stability. Enthalpy of formation, guys. In our curriculum, we have got two types of enthalpy. Enthalpy of formation, which is the formation of a compound from elements. Enthalpy of combustion of any substance, element or compound with the amount or the enough amount of oxygen. Let us first talk about the enthalpy of formation. The enthalpy of formation represents by delta HF, guys. The enthalpy of formation represents by delta HF. The enthalpy of formation or the formation reaction we call as the composition reaction as well. Composition reaction means, or synthesis reaction can be stated as well, means a compound formed from the elements. So the formation of a compound from the elements in their standard form. For example, formation of water. Water formed from the hydrogen and oxygen. This is the formation of water from the, here is given, H2O formed from the hydrogen and oxygen. This is the composition reaction. We mean the formation reaction. But what's the enthalpy of formation or molar enthalpy of formation? Guys, enthalpy of formation in a reaction, in order to equalize the enthalpy of a reaction to the enthalpy of formation, there should be two conditions. First, a compound, 1 mole of a compound must be formed in the product. The general form is that 1 mole of a compound. From what? From the elements that they composed and they form that compound. From the elements. 1 mole of a compound from the elements. So, is the enthalpy change that occurs when 1 mole of a compound formed from the elements. Two conditions. 1 mole must be formed from what? From the elements. We'll be providing the examples, guys. Enthalpy of formation are given for the standard status, guys. Standard state. Standard state, STP, we mean standard temperature and pressure. We measure the enthalpy of formation, or we calculate the enthalpy of formation at standard temperature and standard pressure. Standard pressure usually is 1 atm. Standard temperature is 25 Celsius or 298 Kelvin. The standard status of water is liquid, so the enthalpy of formation must be a liquid for water. Gas and solid is not a standard form of water. The standard state of iron is solid, not the liquid or other states. The standard state of the diatomic molecules are gaseous, such as H2Cl2, except Br2 and I2. Br2 is liquid and I2 is solid. Standard state of single element are solid, such as iron, carbon, except mercury. Most of the elements, they are solid, except the mercury, which is liquid. To signify that a value represents measurements on substances in their standard state, this sign should be used. This is a sign for represents standard state, guys. So whenever we write delta H with this sign, means what? Means enthalpy of the reaction in standard state. So standard enthalpy of reaction. How about how to write the standard enthalpy of formation representation? Delta HF represents to what? Represents the F represents the formation. The H represents the enthalpy, and this sign represents the standard. So delta HF with this sign represents what is standard enthalpy of formation. And we can find the standard enthalpy of formation in table A14. We have a table for the representation of standard enthalpy of formation. Guys, let us test whether the above equations, that delta HR is equal to the delta HF. Delta HR means, we mean the enthalpy of reaction. Carbon reacts with oxygen to form 1 mole of carbon dioxide. Guys, carbon dioxide, 1 mole formed. This is the first condition. The second, from the elements that they form with carbon dioxide, carbon and oxygen. So the enthalpy of formation is equal to the enthalpy of the reaction as well in this case. But have a look on the second one. The 2 moles of water formed from the elements. It has one condition but missing the other one. 2 moles formed, there should be 1 mole in order to equalize the enthalpy of reaction and formation. But it has another condition, that from the elements. So there should be both. Here in this case, we cannot say this is the enthalpy of reaction. It's not equal to the enthalpy of formation. Why? Because 2 moles formed. How to convert this into be in the form of formation? You have to multiply or divide the reaction, that this 2 becomes 1. How? What to do? Divide by 2 all the reaction with that enthalpy as well. So whenever you divide by 2, hydrogen becomes 1, oxygen becomes half, H2O becomes 1. So here 1 H2O formed from the elements. That's why delta HF is equal to delta HR in this case, is equal to delta HR enthalpy for the reaction, guys. The other example, 1 mole of a compound formed. But guys, there should be the other requirement also from the elements. The CO is not the element, it's a compound. So you have to know that in this case the delta HF is not equal to the delta HR. Why? Because the compound 1 mole formed, but not from the elements. Elements carbon and oxygen. This is carbon monoxide and oxygen. In this case, the enthalpy of reaction cannot be equal to the enthalpy of formation, and there is no way to change the condition of this reaction to equalize the enthalpy of reaction to the formation. But whenever the missing requirement is in the amount, we can change the amount. But if it's in the reactants, not from the elements, from the compound, we cannot change the conditions of the reaction to equalize the enthalpy of reaction and enthalpy of formation. Enthalpy of formation equals the enthalpy of reaction when 1 mole of a compound formed from the elements. Both conditions must be met in order to equalize those two. So as you can see, the enthalpy formation for CO2, not predictable because CO is a compound. Enthalpy of formation, sometimes called as the heat of formation, as the enthalpy of reaction calls enthalpy heat of reaction. The elements, guys, like the diatomics, F2, Cl2, Br2, I2, O2, N2, H2, these elements with the other elements, they have an enthalpy of formation of 0. We'll be talking in the stability in detail, but they have an enthalpy of formation of 0. This is table A14. The enthalpy of formation for many compounds is given in the table. As you can see, the enthalpy of formation of graphite carbon is 0. Okay, guys, why? Because it's element. For oxygen is 0, it's element. Why 0? Because we are just able to form compounds. We are not able to form elements in nature. So because of not being able to form elements, we do not have enthalpy formation for the elements. The enthalpy formation can be calculated or is specified for compounds only. Okay, guys. Let us write the enthalpy of formation for these reactions, but we have a note here to write the enthalpy of formation. Always write 1 mole of a compound in the product from the elements. 1 mole of the compound from the elements. For example, here we have got C6H6. 1 mole of this must be in the product from the elements carbon and oxygen, hydrogen. So, for balancing, do not adjust the coefficient of the product. Adjust or balance by adjusting the coefficient of the reactant, guys. Here there should be 6 carbon and 3 hydrogen. That's the enthalpy, the equation which represents the formation of benzene. Another one, NH3. From 1 mole of NH3 from N2 plus H2. To balance the equation, we have to adjust the coefficients of the reactant 1 over 2 N2 to become N, and then 3 over 2 hydrogen to equalize to the hydrogen in the product. The same for the methane, CH4 must be in product 1 mole, and from carbon and hydrogen, guys. So 2 hydrogens. These are the equations which represent the formation of the compounds. FeCl2 from Fe and Cl2. That's the formation of 1 mole of a compound from the elements. That's how we can write the enthalpy of formation, equation for the enthalpy of formations. Which of the following is not thermochemical equation? We said thermochemical equation is an equation that must represent the enthalpy in the reaction. So you can say the first one represents, the last one does not represent, so the last one is not a thermochemical equation. Stability and enthalpy of formation, guys. In the beginning of the session, we talked about the stability in the courses of reaction for exo and indo. We said the stability changes with the energy inversely proportional. As a state has a high energy and a position, a system has a high energy, it has a least stability. But a system with low energy has a high stability, guys. First, let us provide some notes, guys. Elements in their standard state are defined as having enthalpy of formation of 0. We said we'll be talking about this is here. There are elements like H2, O2, F2, Cl2, sodium, iron, zinc, potassium, aluminum, any element in their standard state, they have a 0 enthalpy of formation. Second, if a compound has large negative enthalpy, a high negative enthalpy, this represents the formation of that compound is very stable. For example, formation of CO2 is minus 303.5. It's a large negative enthalpy. And exothermic processes, they are stable usually. Why? Because exothermic means the system releases or emits the heat. Whenever it releases heat, energy reduces in the system, so it becomes more stable. So we can say that the exothermic processes, exothermic is more stable than endothermic. The endothermic is not stable. Why? Because we add heat to the system. As we add heat to the system becomes more unstable. But guys, if a compound has a positive enthalpy formation or slightly negative, the compound represents what? Unstable. It becomes unstable. Like what? Like formation of HI. Formation of HI is, we have 3, guys, usually the formation processes or formation of bonds is exothermic process, but we have three exceptions which the formations are endothermics. So guys, we have three examples or three formation processes which are endothermic. The first one is the formation of HI. The second one is the formation of ethane or acetylene. The third one is the formation of mercury fulminate. We'll be talking about them in detail. In this case, guys, the formation of HI, 1 mole formed from H2 1 over 2, 1 over 2. This formation has a positive enthalpy of formation of 26.5 kilojoule per mole. Positive to 26.5. This represents unstable. Why? Because we have added 26.5 kilojoules to the system. It's unstable. Which one below is most stable? Most stable, if it is in between the negative and positives, you choose the most negative one, guys. The first one, positive, then negative, then positive, then positive. In here, the positive, negative, positive, positive. The positives must be cancelled out with the negative. So the negative is the most stable among all the positives. The negative is what is the most stable. So if it's among the positives and negatives, the negative is more stable. But if it's among the positives, for example, 26.5, 10 kilojoule, 75 kilojoule, 150 kilojoule. Which one is the most stable? The least one. The least one of the positives. So 10 is the most stable. But if it is 26.5 negative, minus 10, minus 75, minus 150, the most negative is the most stable, minus 100 negative. So guys, a simple technique can be used to represent this. 0. If the number goes farther from the 0 and here comes closer to the 0. In the negative side, this is the negative coordinator, that's the positive coordinator. If a negative in the positive coordinator approaching towards 0, the one which is closest to the 0 is the most stable. The one farthest from the 0 is the least stable. But in the negative, it's just the opposite. The one closest to 0 is the least stable. The one farthest from the 0 is the most stable. That can be used to understand the stability if the values is given. The formation of HI we said is 26.5 is endothermic. The formation of C2H2, guys, which is acetylene or ethane, we'll be talking about this in chapter 9. Guys, this is from carbon and hydrogen. The carbon should be 2 here, and then that's a balanced equation. This formation has the positive enthalpy, which is 226.7, and the formation of mercury fulminate, which is HgC2H or N2O2 from Hg plus C plus N2 plus O2. To balance, there should be 2 carbon. That's balanced equation. The formation of mercury fulminate has a positive enthalpy, which is 270 kilojoule per mole. So guys, these two are unstable. The ethane is very unstable, reacts with oxygen and must be stored in cylinder as a solution in acetone. Must be stored in acetone to be away from the air because it reacts vigorously with oxygen. The mercury fulminate, it's used because of its instability, it's used as a detonator for explosives, as explosive agent in explosive bombs. According to the enthalpy, guys, we have a note here. According to enthalpy, the direction is toward the exothermic side. Because substances in nature want to have minimum energy and become stable. So if it is A plus energy goes to B, this is endothermic. Endo by forward. How about reverse? Reverse is exothermic. Always the exothermic side is favored according to a reaction. So in this reaction, which direction is favored? The reverse is exo and reverse is favored. How about another example? A goes to B plus energy. So this is exo for the forward and endo for the reverse. The forward is favored. So guys, simply we can say that for all of the endothermic reactions, the reverse is favored according to enthalpy. For all of the exothermic reactions, the forward is favored according to the enthalpy. Let us talk about the second type of the enthalpy, which is the combustion, enthalpy of combustion. Guys, enthalpy combustion, the enthalpy of formation, it was used only for compounds. But here, the enthalpy of combustion can be used for both compounds and elements. Any substance can be combusted with oxygen or react with oxygen. As the enthalpy of the formation, enthalpy of combustion has two conditions, but the two conditions is about the reactant, not a product. A combustion reaction produces a considerable amount of energy in the form of light and heat when a substance is combined with oxygen. So the oxygen must be one of the reactant in order to be a combustion reaction. The enthalpy change that occurs during the complete combustion or enough oxygen, this is the first condition, of 1 mole of a substance, the reactant, is called the enthalpy of combustion. So we have two conditions. First, enough energy, or enough oxygen, or complete combustion, and 1 mole of reactant must be combusted. 1 mole of the substance must be combusted. Table A5 represents the combustion of some of the elements and compounds. As you can see, the hydrogen is element, carbon is element, they have combustion enthalpies. And the compounds as well, they have enthalpy combustions. So the enthalpy of combustion, unlike the enthalpy of formation, it can be is for the elements and the compounds as well. Example, guys, here 1 mole of carbon combusted with oxygen to form CO2. So the enthalpy of reaction is equal to the enthalpy of combustion. When the enthalpy of reaction is equal to the combustion, whenever 1 mole of a substance combusts with enough amount of oxygen. The second one, guys, this is element. This is compound. 1 mole of compound combusted with oxygen to form. So this is the combustion reaction. The enthalpy of combustion equal to the enthalpy of reaction in the equation. Have a look on the third, guys. 1 mole of the carbon but reacts with the hydrogen, not oxygen. You have to be noticed in this case. Here in this case, delta HC not predictable because carbon is not reacts with the oxygen gas. Combustion, there should be oxygen in the reactant, always. The other examples, guys, 2 mole of hydrogen reacts with oxygen to form H2O. In this case, enthalpy of reaction is not equal to the enthalpy of combustion. Why? Because 2 moles combusted. In order to change this, you have to change the coefficient of the combusted element or combusted substance to 1. So divide by 1, it will be 1 half. 1 H2O. Here the enthalpy of combustion is equal to the enthalpy of reaction, but the above enthalpy of reaction is not equal to the enthalpy of combustion. The enthalpy of combustion represents by delta Hc with this symbol. The symbol represents what the standard enthalpy of combustion as the enthalpy of reaction. We have a combustion calorimeter we talked about previously. It's a common instrument used to determine the enthalpy of combustion. We have explained this in detail. The properties of combustion, guys, the reaction should be with the maximum amount of oxygen, enough oxygen. Second, the reacting substance should be in 1 mole, and the element when it reacts should have the highest possible oxidation number. I'll be showing this to you. If compound react and contain carbon and hydrogen, guys, it will produce carbon dioxide and H2O always. Example, like the hydrocarbon. All the hydrocarbons, when they combust with the oxygen, they will produce CO2 and H2O. But if the carbon and sulfur combust with the oxygen, they will produce CO2 and SO2. Example, like carbon sulfide here, reacts with the oxygen to form carbon dioxide and sulfur dioxide. If the compound is sulfur and hydrogen, like H2S, reacts with the oxygen will produce always SO2 and H2O. So this should be known to know the products, guys. We have 3 examples. The carbon, when it reacts with oxygen, will produce CO2 and CO. And nitrogen reacts with oxygen will produce NO2. N2 reacts with oxygen will produce NO. Sulfur reacts with oxygen to produce SO2. Sulfur reacts with oxygen to produce SO3. Guys, these 3 elements, the carbon, nitrogen, and sulfur, whenever they react with oxygen, they produce more than 1 compound. Which one becomes a complete combustion? Which one is incomplete combustion? They are all combustions, but some of them are complete, some of them are incomplete. Let us balance the reactions. The above is balanced. Here there should be 1/2. This one is 1/2 nitrogen should be in the react. Sorry, this combustion 1/2 of the nitrogen dioxide must be in the product. Or sorry, 2 multiply 2, here oxygen becomes 2, and then here the NO, 2NO, that's a balanced equation. SO2, SO3, this is balanced, but the SO3, 3/2, balance the reaction. We cannot change the coefficient of the elements. Why? Because it's combustion. We are talking about combustion. We are just able to adjust the coefficient of the product and the oxygen. Guys, in 2 ways we can predict the complete combustions. The first, which one more oxygen used, that one becomes a complete combustion. So the first one is a complete combustion. Or second technique, the carbon in both compounds, in which of them has the higher oxidation number, that will be the complete combustion. Have a look, the oxidation number of the oxygen usually is -2. 2 multiplied -2 is -4. The summation of the neutral compound is equal to 0. This is the oxidation number rules. So -4 plus x, 0, x is equal to 4. The carbon in the CO2 is 4, and in the second one, -2 and 2. So in which one the carbon has the higher oxidation number? In the CO2. Another example, guys, here which one we use more oxygen? In the above one. So this one, the complete combustion. And the NO2 -2, to be 4, and -2, 2. So NO2, the nitrogen, has more oxidation number than the NO. Another example, 3/2 with 1. 3/2 is 1/2 higher than the 1. So this one is the complete combustion. -2, this will be 4. -2, this will be 6. So the 6 is which the oxidation number is the complete combustion. The ticks are the complete combustion and the others are not complete combustion. So that's a technique to determine whether a compound, a reaction is a complete combustion or incomplete combustion. Calculations for the enthalpy. We have two ways to calculate the enthalpy. The first one is Hess's law, which stated that, guys, the Hess's law stated what? Said the overall enthalpy change in a reaction is equal to the summation of the changes for the individual steps in the process. These guys, Hess's law used when two or more equations are given. The steps must be given. When the steps are given, we can use the Hess's law. Enthalpy of combustion is 1 mole of a reactant with oxygen, but the enthalpy of formation is 1 mole of a product from the elements, not compounds. Guys, the enthalpy of reaction is for reaction, and its unit is kilojoule. But the enthalpy of formation is for compounds, and it's kilojoule per mole. The enthalpy of combustion is what? Is for element and compound as well. It's kilojoule per mole. You have to know this information in order to be able to calculate the enthalpies. Guys, the second way is that I'll be talking about the second way, and then I will be solving several questions in another file. Second one is whenever the enthalpy of formation is given, the enthalpy of reaction is equal to what? The summation of the enthalpy of formation of product multiply the mole. The mole is the coefficient, guys, minus summation of the enthalpy of formation of reactant multiply the mole of the reactant. We will be using both ways. Let us take these notes, and then we will be solving questions. Always the product of a combustion of an organic compound are CO2 and H2O. We mean the hydrocarbons. When the hydrocarbon combusts, they will produce CO2 and H2O. All combustions are exothermic, guys, except the combustion for nitrogen. All combustions are exothermic except the combustion of nitrogen, but formation reaction can be exothermic or endothermic. A formation can be exo, but most we can say all of the combustions are exothermic except the combustion of nitrogen. Unit of enthalpy is kilojoule, but enthalpy of formation and combustions are kilojoule per mole. The enthalpy of reaction is independent on the steps that reaction occurs, not depends on the steps. Enthalpy of reaction is for all reactions, enthalpy of formation only for compounds, enthalpy of combustion is for element and compound. This is what we stated about. I will be solving here we have got a sheet of questions. The first one, we'll be solving several questions, and I will be showing how to solve those questions. First one, let us practice the first, guys. It's a sample problem. Said, calculate, let me zoom in. Okay. Calculate the enthalpy of reaction for the combustion of nitrogen monoxide gas. Combustion. So whenever it says combustion, how to write the reaction? Combustion of nitrogen monoxide with the oxygen. To produce 1 mole must be combusted. And or to form nitrogen dioxide. What will be the formation? The formed compound NO2. To balance the equation, we are not able to adjust or change this. We are just able to change the coefficient of the other. Why? Because it's combustion. So simply, in order to balance the reaction, we can say 1/2 oxygen. That will be balanced reaction. Said, calculate the enthalpy of this reaction, or we can say the enthalpy of combustion of nitrogen monoxide when two steps are given. 2 steps. Guys, tip can be stated except the oxygen or in some the other problems we have chlorine, except the element which repeated in all the steps, what elements or substances do we have in the reaction? There should be the same number of the steps in the reaction. Here, except excluding the oxygen, how many compounds or substances do we have? 1 and 2, so 2 steps must be given. The first step is given and has an enthalpy of formation of 90.29. The second one, enthalpy of formation 33.2. Let me solve this question can be solved by both ways, the equation and Hess's law. Let me show you how to solve the Hess's law. Guys, for the Hess's law, we have to adjust the steps in a way which the elements or the compound is in the main is in which side, in the step must be in that side. If it's not, we have to reverse it to put in that side. And second, the mole of the element in the main equation with the mole of the element in the step must be equal. If not, we have to multiply or divide the step by the factors. Let us do it, guys. The first one, what do we have in the main equation? How to know which one is the main equation? Always the one that's required is the main equation. We have got NO, except the oxygen. We will not consider oxygens. NO and NO2. So NO in the above steps is in which step? Is in step 1, 2, is in the first step. Is in which side? Product side. In the main is in which side? Reactant. 1 mole, 1 mole. So the mole has no problem. But we have to reverse the step in order to be in the same side as the NO. So reverse the first. Reverse the first step. And we write it. It will be NO 1 over 2 N2 plus 1 over 2 O2. And the enthalpy of the formation must be reversed minus 90.29 kilojoule per mole. So you have to reverse the enthalpy, don't forget. Second, guys, NO2 is in which side? In the main product. In the equation is in the product. 1 mole, 1 mole. So rewrite second unchanged. Second equation unchanged. Second equation 1 over 2 N2 plus O2 will produce NO2, and the enthalpy of formation is 33.2 kilojoule per mole without any change, because we did not reverse or multiply the reaction by any factor. So guys, if you add these two, we will be able to get the reaction. How to add the reactions? Of course, those chemicals which they exist in opposite sides in different steps, they must be cancelled. But in the same side, reactant, product, we have to add them together. Have a look, guys. 1 over 2 N2 here in this reactant, in the others is what? In the product. So this should be cancelled out. NO with NO2 cannot be cancelled, guys. And here half O2 with 1 O2, the half goes with the half, 1 over 2 O2 is a remainder. If, for example, if O2 is in the product, we have to add with the half O2, it will be one half O2. So you have to know how to add the reactions. Here we will get what? NO plus half O2 form NO2, the above equation. And then add these two, you get the enthalpy of the formation. You can add it. I do not have calculator, so add it. You'll get the enthalpy of combustion for the nitrogen monoxide. Oh, guys, simply by Hess's law, it's not necessary to write, reverse, multiply, or write the reactions. Just apply the rule on the enthalpy. NO is in the reactant, here in the product. So reverse it, just reverse, it becomes minus. And then NO2 is the product, so unchanged. Add them together, you'll get the enthalpy of the reaction. That's simply for the multiplication, the multiple choices, guys. The multiple choices, you'll be able to solve it. How to solve this? By the equation, guys. The equation said the enthalpy of a reaction is equal to the summation of enthalpy of formation of product minus reactant. What do we have in the product? NO2. What do we have in the reactant? NO. About oxygen? Oxygen is element, has the enthalpy of formation of 0. So the elements, they have enthalpy of formation of 0. The enthalpy of NO2, the formation is given, that's NO, and the NO2 is given. NO2 is what? 33.2. Multiplied by 1, so will not multiply. The coefficient is 1. If the coefficient is 2, you have to multiply by 2. If 3, multiply by 3. If half, I'll multiply by half. Minus the enthalpy of the reactant, formation of reactant, 90.29, multiplied by 1 because it's 1. So you'll get what? You'll get the same value as the Hess's law. Let us solve more questions, guys. More questions. Here the reaction is given. The enthalpy of formation, the steps, the overall reaction is given. The enthalpy 1 is equal to A, enthalpy 2 is equal to B, enthalpy 3 is equal to C. According to this equation, what's the enthalpy of reaction for this reaction? CO plus H2 CH3OH. Guys, we will adjust the steps according to the Hess's law. CH3OH is in which side? Is in the product side. Here is in which side? Reactant side. So you have to reverse it. If you reverse, enthalpy will be minus A. So this is minus A. Okay. CO is in which is in the reactant. Here reactant. So let the B stay unchanged and B. So the B unchanged. H2 is in which side? Is in the product. Has how many moles? 1 mole in the step. H2 is in the reactant. Has how many moles? 2 moles. So you have to reverse it to be in the reactant and multiply by 2 as well. So it will be what? Minus 2C. Because it will be 2C, and reverse it, it will be minus 2C. And which one is the correct? Minus A plus B minus 2C, minus A plus B minus 2C is the correct option. Another reaction, this is the ministerial exam question, guys. The standard enthalpy of formation of SO2. How to write the equation? SO2, 1 mole formation from S and O2. The enthalpy of formation is minus 297 kilojoule per mole for 1 mole. Amount of released energy when 192 grams of SO2 forms from the elements. The molar mass is equal to 64. Guys, for 1 mole of SO2 which formed, how many energy released? Minus 297 kilojoule per mole. We have to convert this mass into mole, and then we will be able to do the ratio. The mole is equal to 192 divided by 64. The gram divided by gram per mole. So you'll get the number. I guess it's 3 equals 3. Okay? For 3 mole of SO2, how many energy should be released? Find the X by crossing multiple. X is equal to 3 multiplied minus 297 kilojoule per mole. That will be the amount of energy which should be released. Another question, this is a ministerial exam question again. The steps are not given, so we will be writing the steps. Calculate the enthalpy of reaction for the combustion of methane. Combustion of methane. CH4 must be combusted with the oxygen to form what? CO2 and H2O. The enthalpy of this reaction is equal to what? Or we can say enthalpy of combustion, delta Hc of methane. Let us balance the equation, guys. 2 should be there. That's the balanced equation. And then 2 here. Okay. The steps are what? Except the oxygen, there should be 3 steps. To form CO2 and H2O, said to form CO2 and H2O is combusted. If enthalpy of formation of methane, H2O and CO2 equals to these numbers. How to write the equations, guys? The enthalpy of formation of methane is what? Is CH4 in the product from carbon plus H2 to H2. So the enthalpy of formation for the methane is equal to minus 75. And for H2O equals H2 plus O2, 1 over 2 O2. The enthalpy of formation is equal to minus 286. For the CO2, carbon plus oxygen, the enthalpy of formation is equal to minus 393.5 kilojoule per mole, of course. So guys, by Hess's law, just we have to adjust the steps according to the main equation. How to adjust the steps? Let us do that. Methane is in which side in the main? Is in the reactant. In the step is in the product. So this reverse this, it will be positive 75. Okay. CO2 is in which side? In the product. CO2 is in the product. Stay unchanged. Okay. H2O is in which side? In the product. Here is which side? In the product. We do not change the side. But here is 2 H2O. Here is what? 1 H2O. So multiply this by 2. And add them together, you'll get the enthalpy of the reaction. That's simply for multiple choices. Or we can solve this by what? By the equation, guys. By the what? By the equation. By using the equation method. CH4 with oxygen will produce CO2 plus H2O, 2 H2O, to oxygen. The enthalpy of this is 0, enthalpy of formation. The enthalpy of formation of CO2 and H2O minus methane. So the enthalpy of reaction is equal to enthalpy of CO2 is what? Formation of CO2 minus 393 multiplied by 1 plus enthalpy of formation of H2O multiplied by 2 because it's 2. 2 multiplied minus 286. All this minus enthalpy of formation of methane is minus 75, or we can say plus 75. This will be another method to solve the equation or the enthalpy for the reaction. Another question which ministerial exam, for this reaction 2H2O plus 572 kilojoule produce H2 and O2, the standard enthalpy of formation of H2 is equal to what? Standard enthalpy of formation, the reaction must be in this form. 1 H2O from the H2 plus 1 over 2 O2. How to change the above equation to be in this form? We have to reverse it and divide by 2 as well because the coefficient is 2. So reverse this number. This is positive 572 kilojoule. Okay, positive. Reverse it to be negative 572 kilojoule and divided by 2 you get the result, which is almost equal to minus 286. I guess it's minus 286, the correct answer. Another form of the questions, this is a question in the chapter review, guys. A graph is given. Graphically, we will find the enthalpy of the reactions. This is the step 1, step 2, and the main equation. This is the main equation, guys, which is given above. In this, the enthalpy of the steps and the main is not given, so let us calculate the enthalpy of the steps and the mass through the graph. How to read the graph, guys? Let us calculate the enthalpy of the first step. Guys, the reactant of the step or the reaction must be in one of the lines. This is the first, second, and the third line. Okay. A reactant of the step must be on one of the lines, the product in another line. In between those two lines, that will be the enthalpy of the reaction. That's simple. SnCl2 is on which line? SnCl2 is in the line 1. Okay. The product is what? SnCl2. SnCl2 is on the line 2. So this distance, it has what? An enthalpy of formation of minus 325.1. So this is minus 325.1. That's how we can calculate it. Another one, SnCl2 plus Cl2 formed SnCl4. SnCl2 is on the line 2 and SnCl4 line 3. So in this between, what do we have? Minus 186.2 minus 186.2. The last one, SnCl2 to SnCl4. SnCl2 to SnCl4, line 1 SnCl2 to line 3, which is SnCl4. This between is equal to what? The summation of these two, minus 186.2 plus or minus 325.1. This will be almost minus 500 something. That's how we can calculate graphically, guys. The graphical is important as well. The critical thinking, guys. Let us solve the critical thinking. The critical thinking said we have isooctane. The isooctane is C8H18. Is a major component of gasoline. We use the isooctane isooctane is gasoline. Use the following thermochemical or thermodynamic data. Calculate the enthalpy of the combustion of 1 mole of isooctane. So combustion of 1 mole C8H18 combusted with oxygen to produce CO2 plus H2O. Okay, guys. How many carbon? 8 and then 9. 9 oxygen plus 16, it will be 25. So 25 over 2 oxygen in the reactant. Okay, guys. The steps are given. 3 steps are given. The step 1, step 2, and step 3. Remove the oxygen in the for the adjustment process. The isooctane is in which side? In the reactant side. The first step has isooctane and in the product side. So you have, it's negative 224.13. You have to reverse it, it will be positive. This is first. Second, CO2 is in the second equation, second step. Is in which side? Product. Here product. The side has no problem. Here it has 1 mole. Here 8 mole. Multiply this by 8. So the second must be multiplied by 8. The first one, H2O is in the product, 9, 1. So you have to multiply this by 9. The first, multiply the first by 9, second by 8, reverse the third. I guess, as I remember, the summation is equal to minus 5,100 kilojoule. This will be the enthalpy of the reaction, or we can say if it's in the mole of the combustion, kilojoule per mole. This is part 1. We calculated the enthalpy of combustion of 1 mole of isooctane. Part B, guys, said 1 gallon of isooctane has a mass of 2.6 kilogram. What's the change in enthalpy for the combustion of 1 gallon of this? So 1 gallon is 2.6 kilograms. If we combust 2.6 kilogram, what will be the formation of the heat? 1 mole produced minus 5,100 kilojoule per mole. 1 mole of isooctane C8H18 How to convert this into mole by molar mass? So the molar mass of carbon is 12, hydrogen is 1. 12 multiply 8, 80 and 96 plus 18, it will be O will be 114 grams per mole. 2.6 kilogram, we have to convert into gram because the molarity, the molar mass is in the gram per mole. So the mole is equal to 2,600 grams divided by 114 grams per mole. Gram and gram cancel out. As I remember, we calculated it's 22.8 mole. Okay, the number you can check it again. 22.8 mole of C8H18 will combust. How many energy will be released? Multiply this two, you'll get the amount of the energy that will be released through this process, guys. That's the end of the section. Thank you for the attention, guys.